What you see in the background is already part of what I would present to you. It is the so-called Energy Lab, which is a large-scale infrastructure at... a little bit loud. Does it work? Okay. A large-scale infrastructure some 25 kilometers south of here. It is to investigate, from a systemic perspective, energy systems of the future, mainly driven by renewables. Thereby including aspects of sector integration, which means also power to mobility in both directions, so vehicle to grid, grid to vehicle, but also power to X in the sense of power to hydrogen, power to methane, power to liquid fuels. It means also power to heat and the coordination aspects of computer science and informatics with respect to that sector integration. It has a total investment of 30 million euros paid by the German federal state, and the annual budget is around 6.5 million, and it's part of the Helmholtz Association, as I said. Here you have a small overview. In blue, everything which deals with electricity. Now I try to get a pointer on here by doing this. Hopefully it works. Does it work? If not, no. Then I have to point. We have a large solar power storage park having more or less 1 megawatt peak in photovoltaic modules, and a lithium-ion battery storage system, which is in the same size, so more or less around 1 megawatt and 1 megawatt hour. We have redox flow batteries, flywheels, solid oxide fuel cells, gas turbines, which already combine energy in the carrier form of molecules, that is all in green here, with electricity. So talking about molecules, we have several electrolysis facilities, so low temperature and high temperature, even syngas from high temperature co-electrolysis. We have methanation on a high efficiency level, 80%. E-fuel synthesis, some direct air capture. In red, all about heat. We have an own geothermal energy plant at Karlsruhe Campus North, and a high temperature heat storage system together with DLR. In yellow, and this is my main responsibility, we have everything which is the interaction of information and computer science, which is needed there. Also our electric vehicle questions in a lab with electrotechnical devices, and what we call living lab experimental buildings. You will see them in some seconds. So we have built 3 houses together with electrical charging capacities for vehicles in order to study the interaction of grid and mobility and heat in real houses. And what we call, additionally, the Smart Energy System Simulation and Control Center, which has 6 sub-labs for all of these orchestration issues. So these are the 6 sub-labs. We have what we call the Control Monitoring and Visualization Center, which is there for new software for control center for the use in Smart Energy System. We have a real control center there. Then the 3 buildings I just talked to you about, which have direct heating, heat pump heating, and a fuel cell for heating. They are full of sensors, where we do smart home management, studying, they have PV modules on rooftop, studying how can they be grid friendly, how can features as vehicle to grid, grid to vehicle issues help to support grid stability, for instance. Then Security Lab Center, the cybersecurity aspects I was just talking about, headed by Gada Elbes here present. Then what we call the EXAL, so this is about the design, operation and digitalization of future energy grid, where we do real-time simulation even of large grids, so starting from the house to continental level. We have grid replicas in simulation for Europe and for Germany on several integrated levels. Then the Smart Energy System Control Lab, headed by Friedrich Wiegel, who is here, about the investigation of new control and automation algorithms for grids and their stabilization, microgrids, house street interaction grids and then larger grids, with power hardware in the loop facilities up to 250 kilowatt, thereby DC included. We have DC elements. And a larger power hardware in the loop, this is more about device under tests, which go then up to 1 megawatt devices and even higher voltages, together with the colleagues from another institute, which is from technical physics. So I just talked about device under test in power hardware in the loop environments, where, for instance, the lithium-ion battery storage system is part of, or the flywheel energy storage system. We combine this idea of power hardware in the loop. I presume that everybody knows about power hardware in the loop in this room, yeah? If not, then just ask me after my talk. We have a system under test question where we have these kind of microgrid setup, which is flexible and which can be used by perhaps you, because their electromobility is part of the integration. And then in a distributed real-time simulation operation, future power grids going up to the national and to the continental level. And we can combine all of these different granularity, let's say, perspectives for studying the integration of the different levels. What is our available charging infrastructure for vehicle-to-grid? So we have several electric cars with, and we are here with one of these electric cars, evidently. We have several charging points, this power hardware in the loop supply, which is connectable to a kind of copper matrix in which you can, by automation, switch different topologies and configurations for electrical microgrids in order to study these different aspects with respect to stability. We have a known software and monitoring system for this microgrid integration, as well in AC or DC, and the respective charging technologies taking OCPP into account, or ISO 1511 and so on. We have a central backend for central data aggregation, which gives you, together with the fleet of the household, I think a full picture of what we have as hardware and automation in order to do the respective scientific questions. What are these scientific questions? From the car to the charging point to the household to the microgrid distribution network. This is our systemic aspect. So we're not only looking at the car, where we look at the influence of charging algorithms or the car battery as a grid storage or optimization of the car battery, but we go the full systemic dimension to the distribution network, where we then, from a top-down perspective, will think about scheduling, cars for grid control, or the effect of the car charging in the grid from that perspective. Yeah? So this was the other perspective. The charging point, there we have to do studies for the communication between the car and the DSO, so a distribution system operator. So how can a demand-side management be activated in a technical sense for grid support? We analyze the ratio, or the interaction between active and reactive power in the grid. And then what does the charging behavior do to the charging point itself? It's also part of our investigation. With respect to the charging park or the household, we will have the situation in future, and I will say some words about that later on, in which at the household you want to not only to charge your electric vehicle, but also to use in nighttime, for instance, your heat pump, and you have PV on rooftop. So the question is how your behavior as a household user is influencing the overall system of charging, heat pump usage, and other electricity uses in houses. And how can vehicle-to-grid be supportive of all of that? Then for microgrid questions, we look at the interaction between AC grids and future DC grids. One of the three houses we built is a pure DC house, so we can look at direct current applications. There also, again, how does vehicle-to-grid can be supportive, and how the household behavior can be integrated. And about the distribution network, I already gave some aspects. So just to give you an overview, this is the system under test part in which our copper matrix and automation system is very beneficial for yeah, for reconfiguration of topology so that you can use it in a certain sense. We don't have to switch every time new cables, but we have an automated device for clicking in the connections. And this other part is more the device under test perspective. So this real charging infrastructure we use for investigation of real charging characteristics and the interaction with the energy systems. Here we have some results for you, for instance, by using these two cars. With this car, we are actually here. And what we are also are knowledgeable about, others say we are experts, is that we're very good in forecasting time series for parking duration, but also for load forecasting or even generation forecasting from renewables, for residential houses and workplace charging, especially for the duration, which you then need for scheduling and interaction with the grid from a systemic perspective. We evidently also are investigating into optimization and control algorithms for scheduling and grid stabilization. So after having introduced you to that facility, what we have, I want to talk in the next three or four slides about the large perspective we are all in, which you are, from a climatic change perspective, were introduced in the very first presentation this morning. This is a slide I got from Transnet BW, which is our transmission system operator here in Baden-Württemberg, so southwest of Germany. And just from that perspective, they did a study on how will, from their perspective, the energy system, electricity-wise, look like in 2050, in the year 2050. And we will have a generation deficit, according to the study, and I was in the advisory board, we will have a deficit in Baden-Württemberg which rises from 8 terawatt hours to around 60 terawatt hours in that year 2050. So we can be sure about a massive deployment, even here in the south, of wind energy and photovoltaics, because 80% renewables is the goal, at least for 2050, for the net electricity demand by rising electricity demand. I will go to that in the next slide. And we will have a critical bottleneck north-south. Yeah? So from the top-down perspective, the big question, how electromobility can serve as grid supportive, thereby delivering what now is called a certain redispatch possibility, yeah, is one of the big questions top-down. And evidently, if we want to use the batteries built in all of these electric vehicles, we need to have a kind of communication architecture which will allow us to stabilize the grid by using that battery capacities. So this is a big question top-down, and there are evidently questions of cybersecurity and how do TSOs get in interaction with respect to flexibility demand from the DSOs, and how they then coordinate that down to the household level or the electrical car level is a part of our investigation. So now going to the distribution level, we already know, at least here in Baden-Württemberg, we have the so-called Solardachpflicht. I don't know whether you know that in German, which means whenever you have a new rooftop or you refurbish a rooftop, at least 60% must be covered by photovoltaics. So we will have a massive deployment by law, which is also in Germany, the Federal Coalition Agreement, in which envisages 200 gigawatt. Yeah? We're talking about 200 gigawatt of PV power installed by 2030. At the same time, more and more, the question of the heat supply seems to be solvable or should be solved by heat pumps. And that I don't have to talk to you about the rising number of electric vehicles because you know all about that. So electricity becomes a primary energy source. And the question is whether we will go to what is called, as a technical term, the all-electric society. Yeah? So here on the right side you have the sales of the heat pump trends rising here, the installed photovoltaics in gigawatts, and the registered e-mobility, as well battery electric one as plug-in hybrid one. But that is the length of the electrical grid by voltage level, low voltage, medium voltage, and high voltage level. It is fully clear that the question arises, if we go towards an all-electrical society, is the grid capable of doing it? And most people say, oh, the problem starts somewhere at the 110 kilovolt level. And today I have bad news for you, because no, it already starts at the street level. So I talked to you about the Solardachpflicht in Baden-Württemberg, and when I'm talking to the DSOs, so in German Stadtwerke, yeah, they start already to say no to the people who have the PV on rooftop that they cannot connect. And why can't they connect? Here we did a study, a fully fledged electrotechnical simulation with a standard tool. We published that also in the Wonder Conference. Anto Monti raised osmosis together with Andrea. Yeah? And in that study, it becomes clear that this is midday, 12, yeah? That if you want to inject all the power coming from photovoltaics, now in a simulation, we covered that street with more or less with photovoltaics following the Solardachpflicht version. And even if you have small batteries in that houses, the lines in the streets will be overloaded. It doesn't work. And now you can curtail, but that will then in the overall balance not work. So 2 options. One is massively deploy new cables in the ground. We will not be fast enough, and we don't have the workforce. Yeah? So we need to find other solutions, of which using the battery within the cars can be one. Yeah? And the problem not only lies at 12 o'clock in the midday. If we want to go into that future of all-electric society, we have the same situation in nighttime if you at the same time want to use all the heat pumps and electromobility charging at the same time. We believe that a promising approach might be a back-to-back converter-based mesh distribution, so meshing the systems more, because here you see you have an unused part, yeah? And deploying grid batteries even in low voltage level and then orchestrating them. But there again, the orchestration perspective, the systemic perspective comes into play, and this is why I'm here. So what we additionally did with a car manufacturer of south of Germany, we developed a smart charging system with our lab for electric mobility by using the expertise in mobility forecast. In a certain sense, you need to understand the user of that car. Perhaps you even use the information he has in his electrical agenda. Then we talked to that vehicle manufacturer about consumption models and battery models. So you need to have some optimization algorithms for charge planning. And then by integration with information from the distribution system operator, you can do a charging optimization such that as well the grid is supported and as well that the user gets his kilometry he or she wants to have. So this was an overview from what we do. If you want to read and see more, I will leave that now here on screen, and perhaps it's also in the documentation afterwards. To sum up, we're here because we want to provide the systemic perspective from a federal lab background, together with colleagues, especially from Veit Hagenmeyer. We're here for providing you, if you wish, knowledge in as well forecasting algorithms in cybersecurity and in a lab automation and control environment. And we even want to offer you, if you wish, to have a kind of open lab structure. It was erected as an open research platform in order to serve society. Please address us, we are here, and I'm open to your questions now. Thank you for your attention.
Thank you so much. Very, very interesting. Any questions at the moment?
Maybe a question hard to answer, but you show this slide where the 2050 energy consumption is and how we get all the renewable energy. How come that North Rhine-Westphalia has so much offshore wind parks? Do you have any clue? Because
So
they have
first of all, I have to say this is now we have to go back in slides. So how does this work here? Very probably it works like this. I'll try. Yes, it works like this.
Yeah, in this one.
And this one.
You can see that there's North Rhine-Westphalia region which has no access to the sea, but they have a lot of offshore.
No. I think so. First of all, this is TransnetBW who did this study. Yeah,
okay.
It's not my study. I was in the advisory board. But how you have to interpret this is that this is subsumizing the offshore wind parks in the North Sea, whereby this is subsumizing the offshore wind parks in the Baltic Sea. And this is a kind of simplified depiction of their being linked to these offshore parks. Very probably, they also thought already about HVDC direct lines to North Rhine-Westphalia. Yeah, at that part. Because why using the 380, 220 kilovolt grid for transporting the energy where it is directly needed? Yeah? So this is one of the big questions of future grids: is how will be more or less the interaction of AC grids with DC elements. Some think about even a DC supergrid in Europe. Germany would then be a part of it, so that we don't only have line-to-line, point-to-point line connections, but really a mesh DC grid. But up to now, to my best knowledge, perhaps Ante will tell us something differently, no one is capable of controlling such a DC supergrid, because you have 1 degree of freedom less in DC grids than you have in the AC grid, which is the rotary angle at every node. Yeah.
Okay, thanks.
Any other questions? I do have one.
Yeah.
Do you also look at local DC grids at homes?
Yes, we do.
I want one at home, I think.
Okay. So we even have a house for that. So you can come by and you look at it. It's 25 kilometers south of here. We introduce you. You're welcome.
I should. Thanks. Thanks for the